Welcome back. In this set of lectures, I'm going to be talking through what is probably the dominant paradigm of contemporary AI research called machine learning. Often you will find researchers working in AI funded by agencies devoted to funding AI. But when you look at the nuts and bolts of what they do, and when you listen to how they talk about what they do, they describe their work as machine learning. And part of the reason for that is to avoid entanglement with the longer debate about whether an artificial general intelligence is possible, debates about whether AI systems actually are intelligent or not in the sense in which human agents are intelligent. And the thing about machine learning techniques is that these are in the background of most of the really extraordinary business applications and scientific applications of AI. And so a kind of shift has happened where almost all of AI has gotten reclassified as part of machine learning. The only exceptions there possibly are some areas of robotics and the quest for an artificial general intelligence, which, while it might be built on some machine learning techniques, there tends to be an assumption that machine learning techniques are instances of what Searle calls weak AI. They are tools. They are particular, for instance, analogs of human learning or cognitive processes from which we can learn about human learning or cognitive processes, or even more commonly, they're just tools that get a certain job done very well. They give us information. They're an extension of data analysis techniques. And in fact, not all, but almost, well, I'll say many machine learning techniques basically can be thought of as a type of data analysis technique. So a first thing to notice is that the emergence of machine learning as this enormous field of study and as an area where so many new and impressive applications are being developed almost on a daily basis. Part of what's generated that has been a shift in how we use computers or how computers are integrated with our lives. So there has been an accumulation of data sets of the size, and I should say a accumulation in digital form of data sets of adequate size for being able to make use of these techniques, these machine learning techniques that I'll describe in more detail in a moment. And another important precursor or prerequisite of these techniques being useful is the increase in computational power needed to actually work with those data sets and extract valuable information or carry out the requisite transformations of the data in those data sets in order to conduct a revealing analysis using machine learning methods. So this combination of more data, larger data sets, and more processing power makes possible the use of machine learning methods. And so now we're in really a period of boom, of efflorescence, of discovery of different applications of these methods using these large data sets and the currently available computational power. If you think about how scientific research has conventionally been conducted, think, for instance, about Galileo's experiments rolling balls down inclined planes, which form the basis of some of the books that he published on physics, on what are now called kinematics or dynamics. There would be a series of trials, and there would be a certain number of measurements taken for each of those trials. But because of the limits of human beings' ability to collect that data, there would be only but so many trials that it would be, feasible to expect people to conduct. And likewise, the number of features of each of those trials that could be observed and recorded would be relatively small. So a data set consisting of, say, 600 rows, that's 600 trials or 600 examples, 600 cases, where 6 data points were collected about each of those cases, that would be a pretty useful, workable data set according to the traditional, pre-big data kind of scientific paradigm. And still, conclusions can be drawn from data sets of that size. Analyses can be conducted, and conclusions can be drawn, and sometimes experiments need to work with data sets of sizes that small or even smaller. But the world that we live in today is one where there is automatic recording of data, where there is, production of large data sets by virtue of automated methods, or sometimes crowdsourced methods. But it becomes possible to, find oneself wrestling with, say, data sets that have 1 million rows, 1 million cases, or more, and say have 120 different parameters, 120 different features that have been recorded for each one of those cases. You can kind of think of the difference in size here as a difference between 2 Excel spreadsheets. I mean, notice that I've, described this in terms of rows and columns, but that's basically what we're talking about when we're talking about data. We're talking about the kind of information that can be presented in an Excel spreadsheet in almost every case. And so, so you think about the difference in size here, it's not surprising that a different set of techniques might start to be developed for dealing with and for maximizing the value of these larger data sets. Now, there is a kind of single mathematical language that's in the background of a lot of machine learning methods. In a way, all machine learning can be, I say all, a great deal of machine learning can be expressed as transformations on data in tables. So say taking data in a table and then based on an algorithm extracting a certain new value, a new column, let's say, that will be populated by values for each of the items in one's database. In each of the rows will get a new value in this new column, and that the precise value of that variable, or precisely what ends up in that column, will be determined by the algorithm's output based on the input from the parameters in that row. And so the way that machine learning methods work basically is they train the algorithms that transform or somehow process data in the tables so that those algorithms can do better whatever it is someone wants them to do. Okay, whether it's classify the items in the database as being in one of several categories, or whether it's be able to notice a correlation between certain values in the data set and other values, et cetera, et cetera, et cetera. So you can think about what's going on in the background a lot of these methods as basically an application of something called matrix algebra, which is how you conduct transformations on data in tables rather than as is the algebra that we're more familiar with, individual variables and the values of individual variables. But I won't go into the details of the matrix algebra. I just kind of mention it as a footnote so that if you are interested in looking that kind of deeper math component of what we're talking about here up and getting a better sense of it, you can. It's worth asking what defines a program or a process as a machine learning program or process. And I think that the answer to that question is still a bit up in the air. This is such a new field that there isn't just a standard definition of what machine learning is. But my sense of one good way to define it, or at least start to define it, would be to think of this as cases where programs have rules for improving their performance at some task by some metric or some standard. They improve their performance on that task by changing features of their own program, that is, features of the process that they use to extract information from data or to process or transform data. So it's like programs that have within themselves a rule for updating themselves. And there are probably some problems with that definition. Doesn't capture all cases, or it captures some things that don't count as machine learning. But it's a good starting point for getting a sense of what people are talking about when they're talking about machine learning.